So the theorem that I'm going to write here is okay, so we are going to prove that the set is closed if and only if it contains all its limit points. You remember what a limit point is? What's a limit point of a sequence? X star, yes, but X star को definition होगा.
For all x is going to x star f of x.
That's continuing.
But then also x is going to
What's a limit point? We have a sequence x1, x2.
there is a neighborhood around that point such that the sequence every point of the sequence, one point of the sequence will be there in the ball except for x star.
Yeah. So, for if you think of a sequence x1, x2, xn, x star will be a limit point of that sequence if there always exists at least one neighborhood around x star that contains at least one point of the sequence apart from x star. That contains at least one point of the sequence apart from x star. Right? That's the general idea. Sure? Okay? Right. So let's do it. So first, let's start by assuming S is a closed set, in fact. Okay? So we are going to do it two ways. Once we are going to show that if S is a closed set, it will contain all its limit points. And reverse, if a set contains all its limit points, it will necessarily be closed. Because the theorem says if and only if. So it says A implies B and B implies A. If and only if, then it really says that the set is closed, it implies that it contains all its limit points, and if it contains all its limit points, it is closed, right? So it's an if and only if kind of a statement. So first, let's start by checking whether let S be a closed set. So first we'll start with let S be a closed set. Okay, so let's assume that S is a closed set. Okay, so first let's start. What do you want to now show? That it will contain all its limit points. So, think of xn be a sequence in S. Okay? Right? More formally, for how do you write this? For all n, for all n, for all n, xn belongs to S. For all n, xn belongs to S. Okay? Right? Where X is the larger set. X is the larger set. Okay? X is a subset of X. Okay? Sure. So, now what do you have to show? We have to show that x bar belongs to large X, right? So what we are saying is, we have a sequence of points in S, it converges to some point x bar belongs to the larger set. We have to show that x bar will also belong to S. we have to show that x bar will also belong to S. X bar will also belong to S because that's what, because x bar is a limit point. No? So what we will be showing if the set S is closed, it will contain all its limit points. So what we will now show is x bar will converge, x bar will also belong to S. Is this clear? Yeah, everybody understands this? Because if we don't show this, then we have no way of showing that S is a closed set. Okay? X bar belongs to X. Now suppose not. Yeah? Suppose X bar does not belong to S. So where will X bar belong to? S complement. Okay? Implies, yeah, X bar belongs to S complement. Now, what is the structure of S complement? Is S complement closed or open? Open. Why? Because by definition the complement of a closed set. Okay. Now, can you develop the theorem from here? So, X bar belongs to S complement. आगे क्या करेंगे? X bar belongs to S complement is open. So what is another definition of an open set? What is another definition of an open set? Each point of that set is an interior point. So X bar must be an interior point of S complement. If it's an interior point, what do you mean? That there exists at least one open neighborhood around X bar which belongs completely to S complement. So no other point of S can belong to that neighborhood. So there exists a neighborhood around X bar which does not contain any point of Xn because all points of Xn belong to S. Which means that X bar could not be a limit point. But we have said that X bar is a limit point. So if such a limit point exists, X bar must belong to S. You see this point? How many of you have followed this argument? 1, 2, 3, 4, 5, 6, 7, 8. How many of you have 9? How many of you have not followed this argument? And how many of you are a linear combination, a convex combination of those who have followed and not followed? So either you follow or you do not follow, or if you are confused in various proportions, which is a linear combination of understanding and not understanding, right? And which is really a convex combination, so which is nothing but so if you take understanding on x-axis and y-axis, then what you really have is a hyperplane, right? So all of you, okay, right? So now. Okay, let me argue this again. What are the implications of assuming that X bar does not belong to S? S is a closed set. So where will X bar belong? S complement. Right? Now what is S complement? Open set. S complement is an open set. What is an alternative definition of an open set? Every point of the open set is an interior. What do you mean by an interior point? Around each point there is an open neighborhood which is contained entirely within that set. That's what we call an open set. So if every point of S complement is an interior point, we call it an open set. Around every point of S complement there must be at least one open neighborhood which does not contain any points of S. Because it contains any points of S, that is not S complement by definition is not there. When I say X bar belongs to S complement and S complement is open, there have to exist at least one neighborhood around X bar which contains no points of S. But in that case, X bar cannot be a limit point of S. Because by the very definition of a limit point, it says there will exist, okay, Fine. There will always exist an open neighborhood around x bar which will contain some points of x apart from x bar itself. Right? So clearly then, x bar could not be a limit point. So if x bar is a limit point, it cannot belong to S complement, it has to belong to S. It has to belong to S. Right? So there is a set of consumption bundles therefore, each of which is affordable. Right? Then and if the sequence of consumption bundles converges to some limit x bar, then the limiting consumption bundle will also be an affordable consumption bundle. Right? Will also be an affordable consumption bundle. Right? Okay. Now we have to show the reverse, no? What we have here showed is, if S is closed, it will contain all its limit points. We have to show the reverse. If S contains all its limit points, it will necessarily be a closed set. If S contains all its limit points, it will necessarily be a closed set, is what we need to. Yeah.
So if that x bar is not a limit point of x, capital X set, right? Then that is the reason it does not belong to S complement. But what if the x bar is an interior point of set X?
Interior point of?
Set X. You know that the x bar, we showed that x bar is not a limit point of set X. That is the reason.
Set S.
Set S.
S is a subset of X.
Right.
S complement. If S is a closed set, S complement is an open set. There is a sequence of points in S. X bar is a limit point of that sequence of points in S. Now if X bar if X bar does not belong to S, it has to belong to S complement. If it belongs to S complement is by definition open. So around every point of S complement there has to be at least one open neighborhood which is contained entirely within S complement. So there are no points of S in that neighborhood. But the definition of X bar as a limit point of S means that there will always necessarily exist a neighborhood around X bar which will contain at least some point of S. Right? But if now X bar belongs to S complement, then there exists at least one open neighborhood around X bar which contains no point of S. Therefore, X bar cannot be a limit point and belong to S complement at the same time. It will necessarily have to belong to, it's a limit point, then it will have to belong to S. It will have to belong to S. Therefore, if a set is closed, it will contain all its limit points, all points of accumulation. Now we want to show it reverse. That is, if a set contains all its limit points, it will necessarily be a closed set. It will necessarily be a closed set. Right? If it's a two-dimensional space, it will be a circle. No? If it's a three-dimensional space, there will be a sphere. If it's just R1, then there have to be just one interval around it.
My is a point on the border of any particular set S, and then don't exist any space.
Yeah, therefore the whole idea is that if a set is closed, okay, if a set is closed, then it will necessarily have to contain all its limit points. Because if it does not contain a limit point, the limit point will have to belong to an open set. And because every point of an open set is an interior point, there will exist at least one neighborhood around X bar which will contain no other points of S apart from X bar. But then X bar cannot then by definition be a limit point of S. Right? Yeah. Sure? No, it doesn't necessarily. You see, for example, what you say, think of the closed space 0, 1, which contains 0 and 1. Yeah? Think of the sequence 1 upon n. Okay? So, what is the limit of that sequence? 0. And 0 is contained within the closed set. It's on the boundary of the closed set. Right? But when you think of 0, you can think of an open interval around 0, which might not be entirely contained within this set, but it will contain some points of the sequence apart from 0. Right? Whereas if I do this, then the limit is 0, but the limit is not contained in this set. It is an open set. Each point of 1 upon n belongs to this set. I'll have to start with n equals 2. Each point of the sequence belongs to the set, but the limit of the sequence doesn't belong to the set. Yeah? Okay. Now, so we have to now show that if S is not closed, see, first we have shown that if S is closed, okay, S is closed, it will contain all its limit points. Now, let us show that if S is not closed, it will not contain also all its limit points. Okay? Okay. Alright. So, S is not closed, which means that S complement is not open. Remember, if S is not closed, S complement is not open. If S is closed, S complement is open. If S is not closed, S complement is not open. Every set doesn't necessarily have to be an open or a closed set. Okay? For example, I can think of an interval which contains 1 and not 0. Right? With a half open, half closed set. With a half open, half closed set. Okay? The whole set X is an open set. Right? So what will its complement? The null set must be a closed set. Right? But the closed set can also be thought of as an open set. So there are these ambiguities. So every set is not necessarily a closed or an open set. There are closed sets which are half closed, half open, which are sets which are closed as well as open, and so on. Right? And we had examples in this. Right? Okay, so S. So if S is not closed, S complement is not open. Okay? So, what does it mean then? If S complement is not open, then think of some X bar belonging to S complement. Okay? So think of some open balls around X. Okay? So think of, so S complement, suppose X bar belongs to S complement. Right? Suppose X bar is the midpoint, X bar belongs to S complement. Okay. Now, the fact that X bar belongs to S complement means that around X bar there exists at least one, okay, that for every open ball epsilon, because X complement, what is X bar? X bar is the limit of the limit point of the sequence. So for every epsilon around X bar, they have to contain an open ball which will contain at least one element of S. Right? Which will contain by because that's the definition of X bar. Right? X bar is the limit point. Right? X bar is a limit point. So around X bar there has to be something. but x bar belongs to S complement, right? Okay, so think of so do you see a contradiction here? I don't need the next line. So we are done, no? We are done really, because what do we have? If S is not closed, S complement is not open. Right? By definition, what do you have? X bar belongs to S complement because X bar does not belong to S. Right? Okay? So around every X bar by definition, you have a limit point. So basically what it says? It says there is a sequence of points in X, S, there is a limit point X bar and X bar doesn't belong to S. So if S is not closed, right, you will have a point X bar limit point which does not belong to S, which does not belong to S. If S is not closed, right, there will exist a limit point, there may exist a limit point which does not belong to S. So if S is closed, it will contain all its limit points, and if S contains all its limit points, it is closed. Right? So therefore the if and only if part of the theorem. Right? If and only if part of the theorem. Okay. So now what it says is that every feasible consumption bundle, now this is quite important. If you can afford a consumption bundle, right, so this has told us many things. For example, if you think of one budget set of all consumption bundles which are affordable, and if you think of another budget set of all consumption bundles which are affordable under that budget set, right? So if you have M as one income, P dot X less than or equal to M gives you a closed set. Think of M2 as another consumption bundle. Okay, first before that let me ask you a question. We have a closed set, the budget set is a closed set. Will the budget set also be a convex set? Why? A, because of the separating hyperplane theorem, which says it will divide the space into two half spaces, both of which are closed and convex. What do you mean by the budget set being convex? If there is a consumption bundle which is affordable, another consumption bundle is affordable, a linear combination of those consumption bundles will also be affordable. Right? Can you formally prove that to me? So if you have P dot x1 less than or equal to M, yeah, and P dot x2 less than or equal to M. So x1 and x2 are two consumption bundles which are affordable. Can you prove to me that any linear combination of x1 and x2 will also be affordable? If P of x1 is an affordable consumption bundle, if x1 is an affordable consumption bundle, by which we mean P dot x1 is less than or equal to M, right? P dot x2 is less than or equal to M. We are really studying the properties of the budget sets, really. But we are doing it in a more formal mathematical way. So can you tell me any linear combination of x1 and x2 will also be affordable or not? Prove it formally. Okay. So think of the linear combination of x1 and x2, right? Okay. So we have P dot lambda x1 is less than or equal to lambda m by multiplying lambda on both sides, right? Right? Sure? Now let me add the two equations. If I add the two equations, what will I get? If I add the two equations, what will I get? Yeah? If I add the two equations, this is what I will get. Sure? What will cancel? So this lambda and this lambda will go. Right? So what do I have? I have P into lambda x1 plus 1 minus lambda x2 less than or equal to m. Right? But what is lambda x1 plus 1 minus lambda x2? A linear combination of x1 and x2. Right? So it says if x1 is an affordable consumption bundle, x2 is an affordable consumption bundle, any linear combination of x1 and x2 will also be an affordable consumption bundle. Right? That is, budget sets are convex. Right? Okay. Now if you think of one budget set, so P dot x is less than or equal to m, is a set of all consumption bundles which are affordable. Right? Now change P a little bit. Prices change. So there will be a different set of consumption bundles which are affordable. What do you think of the set of consumption bundles which were affordable in the earlier prices as well as the newer prices? So first prices were there, some prices were there, P1, P2, Pn, and a set of consumption bundles which you could afford. Right? Now prices change. There is a different set of consumption bundles which you could afford. But some of the older consumption bundles also could be affordable. So now you must tell me, what do you think will be the properties of the set of consumption bundles which were affordable in the previous prices as well as the newer prices?